So today I have the great honor of speaking with Tom Griffiths. Tom is the Henry R. Luce Professor of Information Technology, Consciousness, and Culture at Princeton University, where he also directs the Computational Cognitive Science Lab. Tom studies many questions related to the relationship between human cognition and computation, with a particular focus on Bayesian approaches. He's also the author with Brian Christian of Algorithms to Live By. Here we go. Algorithms to Live By, the Computer Science of Human Decisions. Tom, thank you so much for joining me.
Thank you.
As I mentioned to you, I think the goal of the conversation is going to be to discuss about how thinking about the mind in computational terms sheds kind of interesting light on what it means to be human, the relationship between human and machine intelligence, and then of particular interest to the Psychology of Technology Institute, how we might live with intelligent machines going forward and how we'll negotiate that relationship. So if you wouldn't mind, just to begin, could we start with a kind of potted history of the cognitive revolution and how it came to be that we came to think about minds as computers? And you might also just throw in Marr's 3 levels of analysis as a kind of organizing principle there.
All right, so we're going to do a semester-long course. That's the idea here.
Hopefully I can speed run through this, but I want to give as many people a background who might have it as possible.
Okay, so I mean, the cognitive revolution had a lot of parts, but one of those parts was the discovery that you can use mathematics to make formal hypotheses about how minds work that then turn into testable predictions that we can explore in the lab and through other methods of interrogating human behavior. So to put this in context, right, in the 1950s, the kind of dominant way of studying the mind at the time was not to study the mind. It was this behaviorist approach to psychology, where the idea was that you're going to get scientific rigor from eliminating internal stuff and just focusing on external stuff. So focus on the stimuli that people see, the responses that they make, how it is that environments shape our behavior, and sort of learn these stimulus response relationships and so on. And so the cognitive revolution was the idea that, no, actually, we need to talk about these internal states, and we can talk about these internal states because we can be rigorous about the way that we do that if we use certain kinds of formal ideas to allow us to give us the sort of vocabulary for making precise hypotheses that we can then test, right? And so things that I see as emblematic of that were like Chomsky's approach to language, where he said, let's use formal language theory as a way of expressing hypotheses about the nature of language that we can then interrogate against our own intuitions about things like grammaticality. Miller's Magic Number 7 paper, right, which is kind of saying, okay, let's use information theory to make precise information about, ideas about how much information humans can process and store. And then Alan Newell and Herb Simon's work on the logic theorist, which said, we can have concrete, explicit hypotheses about complex cognitive processes like problem solving. We just express those in the form of computer programs, right? And so those 3 instances are all kind of like illustrations of this idea of using math as a way of getting precise hypotheses. Okay, so we'll fast forward now another 30 years. So when we make computational models of cognition, right, which is something that we now do a lot in cognitive science and psychology and other related fields, we have a choice about how those computational principles are being used. So if you look in those sort of early models that I talked about for Newell and Simon, what computation was actually a kind of potentially a description of explicit cognitive processes, right? For Chomsky, it was something much more abstract. It's sort of like the math that he was using was describing something abstract about the properties of languages and not necessarily anything concrete about the actual processes inside people's heads. And so, about 30 years after people started doing this, David Marr introduced this sort of analysis of the different levels at which we can propose these computational models, right? And so Marr's 3 levels are famously what's called the computational level, right? Which maybe is a little bit confusing because we're talking about computation at all of these levels. You could call it something more like the function level, where it's about you're using math and thinking about sort of abstract computational problems as a description of the thing that human minds have to do, right? So an example of this would be something like saying, my computational level theory of inductive inference is Bayesian inference, Bayes rule, right? Where that's a piece of math that tells me what the right answer is to certain kinds of questions. Then there's another level of algorithm representation. That's where that abstract description gets cashed out in actual algorithms and actual representations for solving those problems, right? And so those could be whatever you think the cognitive processes involved in inductive inference would be, right? And then a level below that is the level of implementation, which is saying, now we're going to talk about the sort of computational aspects of how those algorithms and representations are instantiated in things like brains or silicon chips or whatever the mechanisms of computation might be, right? And so now it's like, how does the brain execute these algorithms for probabilistic inference, right? And so whenever we're making models of cognition, it's always good to be explicit about what level of analysis we're operating at. And I think those levels are designed to be sort of mutually constraining. The answer to the question of what's the abstract computational problem you're solving becomes information about what those algorithms have to be doing, becomes information about what it is that neurons have to be doing, right? And they're designed to be things that kind of give us tools for asking questions more precisely, and also recognizing some of the time when we might be developing theories and those theories aren't in conflict with one another. So like, I can have my Bayesian theory at the computational level, and you can have your neural network theory at the algorithmic level, and those theories can be still, sort of compatible in the sense that we think about what that neural network is doing is solving a computational problem where the solution is described by Bayesian inference, but then the mechanism is that neural network.
And thinking about things at the computational level, I would imagine is also how you get a common language for speaking about what human beings are doing and what AI systems are doing, whereas at the implementational or algorithmic level, those things might differ widely.
Yeah, I mean, I think there's the potential for connections at all of those different levels of analysis. So, but it's, you could think about it as like the opportunities for divergence increase, right? So at the computational level, if you think about sort of like, a good analogy here is something like convergent evolution, right? Like human eyes and octopus eyes operate by very similar characteristics, but are derived through very different, biological routes, right? And they, have those similarities in common because they're solving a shared computational problem, right? And so computational problems are definitely things that we can agree on with computers. Algorithms and representations, we can agree on to some extent, although we might be operating under different constraints from the constraints that a machine is operating on, and those are going to influence the kinds of algorithms and representations that we end up with. And then implementation, I mean, mostly we're talking about computers implementing things in silicon and brains implementing things in neurons, and you can imagine ways in which those might meaningfully diverge. But you can also be somebody who wants to do neuromorphic computing and draw inspiration from the structure of brains to design next generation silicon chips.
Okay. So I sort of want to circle around this question of like why is the computer metaphor for the mind much more than just a metaphor, right? And we've gotten into that a little bit already. But part of what makes people resistant to this idea that minds are computational is this kind of constrained image of what computation is, that it's this kind of disembodied, rational calculation, as you said, explicit. There's a sort of formal symbol manipulation conception, and this has evolved through the history of cognitive science and the history of AI, just different ways of thinking about what the relevant definition is of computation is that we're dealing with. So to bring in Bayesian approaches, what's the best way of putting this? One kind of thing that's emerged from this is the idea that human beings are sort of hopelessly irrational as compared with computers that are, imagined to be these sort of idealized rational systems. And you get things like the heuristics and bias program that says, here are all the ways that we diverge from ideal rationality, considered in a particular way. What does it mean to be rational in the sense implied by Bayesian approaches? And, could you sort of challenge this idea that thinking about minds computationally necessarily means that human beings are kind of irrational by comparison? Does that make sense?
Yeah, there's a lot of pieces there, so maybe we can we can work through them one by one.
Yeah.
Okay, so the first one is about kind of what our conceptions about rational computation look like, right? And I think you know, when you talk about rationality and when you talk about things like computers, people have the idea that, you know, computers, you know, the way that they're going to solve problems is being, you know, sort of deterministic. That is, they always produce the same solution. Exact, that it's always the right solution, right? And those kinds of properties, it turns out, when you sort of get into more advanced computer science, are not necessarily always the most efficient way to solve a problem, right? So what a computer scientist is doing is often trying to think about how to get a computer to think less, right? So like the computer can, in principle, calculate its way towards the solution to a problem, but designing good algorithms often comes down to thinking about how do we get the computer to spend less time thinking, and some of the time, to make it spend less time thinking, in fact, maybe like astronomically less time thinking, you have to give up on, you know, sort of getting deterministic answers or getting exact answers. And so computer science is all about those trade-offs of how do I, you know, how much flexibility am I going to allow in the answer to the question that I'm getting versus how much effort am I going to put into computing it, right? And so that idea that, you know, in fact, what computers should be doing is sort of relatively sort of approximate and inexact. And a really good example of this is like the sort of regimes that are used in like cryptographic algorithms inside your computer, right? You think, okay, that's something where, you know, everything has to be exactly right all the time. But in fact, you know, in order to quickly deal with prime numbers, many of the algorithms that are used are things that are the best algorithms for working with prime numbers are in fact, in some cases, randomized algorithms where you just sort of have a very, 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 very tiny probability that it gives you the wrong answer. And even if it does, it's not that big a deal, right? So, you know, I think step one is sort of reinterrogate our intuitions about what it is that the machines that are sitting in front of us are doing, that it's not always exact, it's not always deterministic. Step two is kind of challenge our conceptions about what rationality is, right? And so rationality, the way that we kind of generically think about it, is kind of an economist's idea of rationality, which is you always take the action that maximizes your expected utility, right? Like you always do the thing that's sort of like the thing that is going to give you the best, on average, give you the best payoff. And that economist's idea doesn't have anywhere in it how hard you have to think in order to find that solution, right? It just says, take the best solution, but it doesn't say anything about like, it might turn out to be completely intractable for you to figure out what is the thing that maximizes your expected utility. And so if you took that as a prescription for actual rational behavior for any finite agent, whether it's a human being or a robot, right? If you built a robot with the economist's definition of rationality, and you give the robot one of those problems, then, you know, it's never actually going to end up making a choice. It's just going to sit there forever crunching away on the problem until it sort of finally gets the solution, at which point, you know, humans no longer exist or whatever happened, right? You know, you like enough time has passed that the question is no longer relevant. And so if you're dealing with real finite agents, you need to have a better theory of rationality. You know, for good reason, artificial intelligence researchers have thought hard about that problem and have a better theory. It's called bounded optimality. It's basically the idea that what it means to be rational is not always choosing exactly the right action, but rather choosing the best strategy for selecting that action, where that strategy trades off, you know, computational cost with the benefit of the outcome that you end up getting. So with that more nuanced and perhaps more useful definition of rationality, we can then go to step three, which is go and look at human behavior and see how humans are doing. And humans traditionally look bad on the classical economist's notion of rationality. They look much better on the computer scientist's notion of rationality, right? So the economist notion is always, you know, maximize expected utility, always act in a way that's consistent with probability theory, you know, that the heuristics and biases program identified all of these things that people would do that are kind of things that they shouldn't do under the prescriptions of expected utility or probability theory. And when we recognize that those are difficult computations, and we take that into account in thinking about the strategies that people follow, the strategies that people follow end up looking much more reasonable, right? So some of the things that we do that result in biases, some of the heuristics that we follow are things that we can actually make sense of from the perspective of this kind of bounded optimality kind of alternative, conception of what rational behavior looks like.
And is there a divergence between sort of Bayesian ways of thinking about that versus like other kind of approaches in thinking about bounded rationality, or do you sort of think of them being like if we're sort of doing the rational Bayesian thing, is that just the same thing as other conceptions of what bounded rationality would mean, or are there sort of different conceptions?
Okay, so I think there's again there's sort of like two steps there, right? So the first part is, how does Bayes look different from sort of some of the things that we might intuitively think about as rational behavior? And so in terms of sort of like formal definitions, Bayes is consistent with sort of classically rational behavior, right? So like you're following a Bayes rule is what you should do as a rational agent who's trying to update their beliefs about the world. But in circumstances where your prior distributions, the expectations that you have about the world, are not aligned with the way that the world is, that can lead you to do things that that are not consistent with classical notions of rationality, right? And in general, what Bayes' rule tells you to do is it tells you to be biased, right? It sort of tells you be biased, but be biased in the direction of your prior distribution. And your prior distribution is supposed to encapsulate the things you think are likely to happen in the world. So being biased towards those things is, a kind of a reasonable thing to do, right? So, so just saying people are sort of acting in a way which is consistent with Bayes' rule, people are being Bayesian, that's not in conflict in any way with sort of, like classical notions of rationality. It might be something that can explain some of the weird things that people do in cases where there's a mismatch between what you think you're asking people to do and what they think they should be doing, right? Or the kind of prior distributions that they're assuming. So I can give you examples of this. So like classic example, you flip a coin 5 times, it comes up heads, 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 right? Versus you have a coin that's heads, heads, tails, heads, tails. Which of those two sequences is more likely, right? And people will tell you heads, heads, tails is more likely. But you could, and that's what you should say if you know probability theory, right? But sorry, what you should say if you know probability theory is that they're equally likely, right? The probability of those two sequences is the same. And so the thing that people are doing when they're telling you heads, heads, tails is more likely is it seems like they're just answering a different question, right? So you're asking them, what's the probability of the sequence given a random generating process like a fair coin? And they're answering the question, but what's the probability that a random generating process like a fair coin was used in generating the sequence, right? And so if you see heads, heads, tails, it's much more likely that it gives you more evidence that a fair coin was being used than if you see heads, heads. Okay, so that's a way that you can use Bayes' rule to explain something that's sort of irrational, potentially inconsistent with probability theory. You say, okay, maybe people are solving the wrong problem here. They have some expectations about the problem that they're solving, such that they're doing the sort of diagnostic reasoning rather than thinking about the probabilities of these events. Okay. What I was talking about when I was talking about bounded optimality goes a step further than that. It says, let's not just sort of be rational about the beliefs that we have, but and the way in which we're updating them. Let's be rational about the computations that we're performing to allow us to update those beliefs. So it's useful that we talked about Marr's levels of analysis. It's explicitly saying, let's push this sort of principle of optimality that we talked about at the computational level, thinking about what people do in terms of the ideal solution to computational problems that they face, and push it to the algorithmic level, where now we say, let's think about what ideal algorithms are for allowing us to approximate that process of probabilistic inference or that process of calculating expected utilities or whatever it is. And when you do that, now you're allowing for the possibility that whatever the constraints we're operating under are, the time constraints, the limitations on the amount of computation we perform, that those influence the answers that we produce in a way which is consistent with the spirit of bounded rationality more generally. But under this approach of bounded optimality, or when we use this as a psychological theory, we call it resource rationality, because it's saying you are going to be rational about the way in which you use your cognitive resources to answer a question. And the rational use of cognitive resources might be something that leads you to make systematic errors, but those systematic errors are kind of like inevitable because of the limits on the resources that you have. And so the difference from other conceptions of bounded rationality is that in this approach, we're saying you are making optimal use of limited resources, whereas generically bounded rationality just says you have limited resources.
Right. And therefore making non-optimal decisions as compared with the sort of idealized picture.
Yeah, so there's a step further, which is to say, yes, you have limited resources, but you're making good use of them. And as a consequence of that assumption that people are making good use of their limited resources, that turns it from a theory that says it's not something, like it's not rationality, to a theory that says it is something, which is that now we can then end up with making sort of generalizable models that produce predictions about the way in which people are going to engage in specific kinds of behaviors in novel situations, right? So sort of that assumption that you're making good use of the limited resources you have allows us to derive models of behavior in novel contexts.
And does that, well, so I see how the strategy for pursuing the goal would change in light of the limitations you're facing. That also changes the sort of goal that you would be pursuing. And I'm wondering, like, how deep does that run if the goal and the strategy are sort of infinitely variable? Do you kind of get at what the intuition I'm pressing on is? You know,
well, okay, so maybe explain a little more.
Well, I'm wondering. I have a whole set of questions about your paper about understanding human intelligence through human limitations. So maybe I'll push it. I'll push it to
okay,
there.
Sounds good.
Okay. One sort of interesting development that's happened over the course of cognitive science and AI research is a changing conception of like what the hard problems are, right? So the kind of earliest conception might have been this Cartesian sense that the hardest thing that we do is this sort of abstract rational calculation, and then that turned out to be extremely easy for computers to do, and then it changed our sense of like what the harder problems would be, like perception and sort of acting in the world as the actual harder problems. Does a sort of Bayesian way of thinking about these questions also shed interesting light on like, okay, here are problems you might have thought were easy before that are in fact difficult, and vice versa?
Yeah, I mean, the way that I characterize this is that it's more that thinking in these terms gives us a tool for demarcating easy and hard problems, right? And so the way that I normally make that demarcation is to say, we can make a distinction between what we can call deductive problems and what we call inductive problems. So deductive problems are problems where you kind of know what the rules are, and getting to the solution is a matter of kind of following those rules, right? So like 2 + 2 = 4, right? Or, you know, whatever it is, right? Like something where you know the rules of arithmetic, you just have to follow through a calculation in order to get there, right? And there are hard problems in that space, but they're sort of computationally hard, but we sort of know what we're trying to do, and it's a matter of just doing enough computation to get us there, right? So chess, you know, arithmetic, theorem proving, you know, some of these sort of things that are sort of classic success stories in many ways for AI systems. And then inductive problems are problems where you maybe know what the rules are, but then we don't have all the information that we need in order to be able to figure out what's going on, right? Or maybe we don't even know the rules in the first place. And so an example would be if I tell you, you know, x + y = 4. What are x and y, right? So sort of classically from a arithmetic perspective, you have 2 unknowns and 1 observed value, and so you can't say anything, right? But if I just tell you, okay, there are 2 numbers and they add up to 4, you can come up with some kind of answer to that question. And what are you going to guess?
It's 0 and 4, 2 and 2, or 3 and 1, and you sort
okay, great. Okay, so you gave me a bunch of guesses there, right? Yeah. Things you didn't say were like pi and 4 minus pi, right? Or, you know, and you didn't say those because for those inductive problems where you don't have enough information to determine the conclusion, you have to rely on your sort of prior expectations, right? And you had a prior expectation. It's like, positive integers. You didn't say like negative, 20 and 24 or anything like that, right? So you had strong expectations that allowed you to nonetheless make a guess. And that's what you need in order to solve those inductive problems, right? So then if you're solving inductive problems, you need a way of characterizing what those expectations are. That's kind of what I think Bayesian inference does for us. So Bayes' rule is a way of putting together the information you have from the data that you observe, right? In this case, something equals 4, right? Two things equal 4. And the prior probability that you assign to different solutions, in this case, what different answers to that question could be, such that it picks out, certain kinds of things with higher probability than others. And so, so inductive problems include perception, learning language, doing science, figuring out causal relationships, right? All of the things that we kind of think about classically as problems that are much more difficult for AI systems, things that humans excel at. And so then that gives us a challenge, which is, figure out what the prior expectations are that guide humans to good solutions to those problems. What machine learning researchers call inductive biases, the things other than the data that lead us to favor some hypotheses over others. And so that sets up a research program of document the inductive biases of human beings and then figure out how to instantiate similar kinds of inductive biases in machines.
And just to draw a parallel to what you were talking about earlier, this is like a way of constraining the scope of the problem to make it computationally tractable for us, by having the way, I could guess every single possible combination of things, but that would leave me like in the position of the robot that you mentioned before of just running through different options. But if I have strong priors and a constrained scope, only check integers, something like that.
Yeah, so you could think about that. I mean, I think generically you need good priors to give you good solutions to a problem, right? The thing that makes you successful is if your prior distribution actually corresponds to the probability with which those solutions appear in the world, right? But it can also be the case that because if a prior distribution narrows down the space of hypotheses enough, right, then it makes it much more computationally tractable for you to solve that problem as well. And so that's I think when I started out working on these topics, I was focused on the first property that it sort of tells you what good answers are. But I think as I've switched to thinking more about computation, like it tells you like, it gives you the right bias, right?
As relative to what's in the world, right?
Yeah, that's right. Yeah.
Okay.
But then, I've been thinking more and more about sort of cost of computation, and then having good priors is definitely helpful from that perspective too. Yeah.
Cool. Okay.
I can give you a nice example of that too, which is in causal learning, people have a sort of expectation that causal relationships are near deterministic. And that is very, very helpful for figuring out causal relationships, right? So like if you look at the cases where people have trouble with causal relationships, there are cases where those relationships are sort of very stochastic, right? But if you're in a situation where, you're flipping a light switch and a light is coming on, the assumption of like near determinism makes it very easy for you to figure out. You don't have to like flick off your light switch enough times that you got a sample size that allows you to do a chi-square test, right? You can actually sort of figure that out from a single observation. And part of the reason why you can figure that out is because of that assumption of determinism.
Interesting. Okay. That makes a lot of sense. So a slightly different angle on the questions we've been talking about. We've been talking about how our sort of conception of cognition has changed and what difficult and easy problems are. I'm wondering if this sort of ongoing dialogue between AI and cognitive science and computer science has also sort of shifted our conception of like what the core thing is that we talk about when we talk about what computation is, right? So like there's sort of different ideas about computation, formal symbol manipulation, Turing machines, information processing is one that gets talked about in cognitive science. Like digital state machines is another one. Like these things have a lot of things in common, but they're not exactly the same, right? Like they don't have sort of exactly the same core idea behind them. So I guess I'm wondering, like, has this ongoing dialogue sort of sharpened our sense of what the core thing is that we're talking about when we talk about computation, and what's the version of it that you're using when you think about whether minds, or the extent to which and the senses in which minds are computational? Does that make sense?
Yeah, I mean, although I think I don't don't ask that question of myself very often, right? Like,
Yeah.
I don't ask, oh, are minds computational? Probably
No,
not.
I
You
know.
know, like it's sort of like a
It's more like, what
implicit
does it mean to
assumption.
say minds are computational?
Yeah.
Given these, because the people who object, the people who say, no, minds aren't computers, often have in mind a kind of straw conception of computation as, say,
Right.
on symbol manipulation.
Yeah. Yeah. I mean, I think that's reasonable. I mean, I think when I say computational, I also often think in terms of like, like Marr's computational level, right? So like, for example, there's nothing in Marr's computational level which makes a commitment to any kind of notion or model of computation. Nothing symbolic, nothing, it's just saying we can give a mathematical description of the problem that we're trying to solve, and then we can analyze behavior in terms of ideal solutions to that problem.
So that's the conception of computation as just mathematical. I mean, or
yeah, and it's a very, yeah, I'd say it's an agnostic idea, right? Because the next step from that is that whatever that solution is has to be realized somehow, right? And then that's when you start having to think about algorithms and like computational architectures and things like that, right? And so I think, again, when I think about, like, in most of the analyses that we do, they're pretty agnostic to those choices about algorithms and architectures and so on. Like, we analyze things like, if we want to think about it, so if we say, okay, at the computational level, I'm going to make sense of human causal learning in terms of Bayesian inference, right? We can set up a problem of Bayesian inference. You need to have a prior distribution over causal structures. You need to have some data that you see. You put those together via Bayes' rule. It tells you which structures you should prefer. And then the next level, the level of algorithms representations, we might say, okay, well, let's assume that you're doing that via some kind of stochastic sampling process, where maybe you've got some current candidate graphs that you're going to consider as causal structures, and then you're going to update those as you get more data. And again, there's nothing there, like, that's an algorithm, but it's not anything that says, okay, now I'm going to commit to some symbolic Turing machine or something like that. We're still operating at a level of abstraction, which is a long way above, I think, any sort of commitment to particular sort of notions about computation. So I think you can talk about algorithms even in a way that's pretty agnostic to how it grounds out, and that's one of the themes of our book, right?
I was going to say, you sort of make exactly this point in the book, that the thinking about algorithms is broadly interdisciplinary, in part because there is no precise sense of what an algorithm is apart from effective ways of solving a problem that have a sequence of steps or whatever else. And it's computer science is informative about it, but the particular ways that algorithms get studied in computer science aren't the only ways you might think about it.
Yeah, I think that's right.
Okay. I guess too, I mean, so on that understanding, in early cog sci, there were sort of these the kind of objections to early cognitivism were framed as like non-computational approaches, but then those things seem to have been subsumed in our sense of what computation is. So like connectionist approaches, like nobody would dare say like a neural network is not computational in some sense now, but when those things were first proposed, they're like, we're doing the non-computational thing as opposed to, as against your kind of narrow sense of cognitivism.
Yeah, or non-classic. I mean, I think they get at particular, again, like intuitions we have about computation, right? So like you can have non-symbolic models, right? Of course, it's grounded out. If you implement it in a in a digital machine, there's some point at which your non-symbolic computation is grounded out in something that's symbolic. But again, the level at which you describe it in terms of math.
I'm sorry, is it symbolic? Well, I guess it depends on whether you take symbolic to mean like representational, right? Because that's another.
Yes, that's right.
Weird, yeah.
Okay. Yeah, and then there's like non-representational approaches. That was where I was going to go next, right? So like ecological psychology or these kinds of things. And again, I think people, there's a workshop at the NeurIPS conference this year, which is on ecological reinforcement learning, right? And it's kind of like, in the same spirit of ecological psychology, although I think maybe a little more representational than the original proposals about ecological psychology. But yeah, I mean, I think those are things where you can imagine them, again, being implemented by a computer without needing to make a strong commitment about, like symbols or anything else. Yeah.
Okay, so I want to both for my own clarity of understanding and for the people who might not be cognitive science nerds who listen to this conversation, just retread a little bit of that. So on one far end, you might have like a pristine symbolic representationalist view where what you're manipulating are these kind of pictures of the world, so to speak. And on the far other end of anti-representationalist views, you're using the world as its own model and kind of bumping up against it. And that's what you were talking about in the context of sort of ecological models. And there are maybe many places in between those two where you're strictly representing it. You have a model in your head that mirrors it more or less accurately. And on the far other end, you don't have a model at all, and you're kind of tumbling.
Yeah, but at the end of the day, we're probably going to use computers to implement all of those different proposals, right?
which gets at this, you know, I get that there's not a sort of strict answer to it, but this question of like, okay, what is the core idea of computation being discussed here? If it can be representational or not, meaningful or not, symbolic or not, you know.
Well,
it sort of just gets to saying like minds are physical. It's not magic or something like that, you know, like.
I mean, I think maybe you can make a distinction between like computation as hypothesis and then computation as some distant substrat that implements something else, right? Like where that classical symbolic perspective is really saying, okay, take the Turing machine, and that Turing machine is our hypothesis about how minds work, right? You're in state, you update that state based on information from the environment, transition to a new state, and so on, right? That's kind of like the classical, you know, sort of computationalist view. Versus at the other extreme, we say, okay, we're going to have this sort of ecological story. You're not building a model of the world. You're just learning what action to take in what situation, and being guided by the environment and doing that. And there might be a computer that's underlying that, right? But the fact that that's a Turing machine is sort of irrelevant to the theory itself, right? Like or von Neumann machine or whatever it is, right? Like there's not that's not a part of the theoretical claim. It's just like that by convenience, using the fact that we have these universal computing devices, that's the way in which we're going to instantiate the theory.
But something like computational complexity limits, which is some of what you're thinking about, that applies whichever other conception of computation you're thinking about, right?
Yeah, although it does matter a lot. So there are kind of there are some kinds of results in complexity theory where it doesn't matter so much what choice you make about how you think about the architecture, but there are other kinds of results which do matter a lot, right? So like when we're talking about some of the things I was talking about before about, you know, bounded optimality and this notion of resource rationality, okay, going to make rational use of my cognitive resources, it really matters what the resources I have are, right? And so when we make those models, one of the assumptions we have to make is about what kinds of computational operations are available to you, what kinds of sort of computational actions you can execute in order to update your beliefs. And so in doing that, we are making a commitment where we're saying, okay, here's my model, you're doing Bayesian inference, you're doing this by sampling. We'll say the basic sort of computational operation you can perform is to draw a sample from a probability distribution, but we're going to charge you every time you do that. Right. And so the way we're going to measure the complexity of that computation is in terms of the number of samples you have to draw. Okay. And now we have a well-defined problem, which is do the best you can at solving this problem of Bayesian inference while minimizing the number of samples that you're drawing. Right. And we can sort of work out what the solution to that problem is. But that solution will look different from, say, if I'd said what you care about is the number of floating point operations you do. Right. And so, you know, now you want to minimize the number of floating point operations and so on, you're going to get a different answer. And so when it comes to actually grounding these things out in sort of hypotheses about cognitive processes, and you are making that analogy between cognitive processes and computations, you need to be precise about what the sort of architecture is and what kinds of computations are available.
Right, and so these kind of 4 ecog-sci approaches that are thinking about embodiment and situatedness and things like that, those are sort of like enumerating limitations that place constraints on what kinds of computation.
Yeah, that's right. Or articulating, maybe sort of reasonably what are assumptions that it's reasonable for us to make about the kinds of computations that are available to us.
Okay, cool. Okay, let's see. Okay, so this provides a sort of helpful bridge to this fascinating paper you have called Understanding Human Intelligence Through Human Limitations. And I guess one way to start would be just thinking about how humans have sort of philosophically throughout history understood themselves by comparing themselves to what they consider to be the closest analog to themselves. It's been animals in the past, right? And so we define our human uniqueness and what our unique capacities are relative to what animals seem to lack. And the sort of starting point that you take in this paper is that AI systems provide a kind of new comparison class for thinking about what constitutes human uniqueness. So with that kind of with that kind of setup, what is different about what AI illuminates about what unique is humans from what animals illuminate about what is unique about humans?
Yeah, so the question that I really sort of started out with here was, okay, let's sort of fast forward to the future and imagine that we live in a world of super intelligent machines, right? Then is there going to be anything which is distinctive about human intelligence, right? And the argument that I make in the paper is, yes, I would say there's going to continue to be a unique flavor of human intelligence, whatever happens with our machines. And that unique flavor is determined by the specific constraints that a human life operates under that determine a class of computational problems that we could consider sort of uniquely human computational problems. And so those constraints I sort into three categories. They are that we have limited time, right? In a few different senses, but perhaps the most fundamental is like, we're only going to be around for about 80 years if we're lucky, right? Or so we have some finite lifetime that we're going to be spending, and that finite lifetime shapes both what it's possible for us to learn from, but also kind of like the time scale on which we're going to have to transition from learning how to do things to actually doing things in order to derive any benefit from it. The second is we have limited computation, right? So we're limited to the 3 pounds or so of neural tissue that we carry around inside our heads. And that is going to fundamentally affect our ability to solve problems, where we're going to have to be really efficient about how we solve problems in terms of reusing partial solutions that we've developed before, recognizing a problem that has some common structure, or just sort of finding solutions that aren't the perfect solution, but are pretty good solutions, in terms of, sort of managing this trade-off between what the quality of the solution we find is and what the computational costs involved it might be. And then third, we have limited communication. So we are forced to communicate about the data that we've experienced and our sort of internal states of our computations using this very indirect method of making honking noises with our mouths, right? And so,
or gesturing with our bodies, or
or writing things down, but those are pretty low bandwidth mechanisms for communicating what's potentially a pretty high dimensional object. And so the point here is that those three sort of families of constraints characterize a set of problems which are quite different from the problems that contemporary, even contemporary AI systems face, where if you are a machine, you potentially have an unlimited lifespan, right? And the future over which you're optimizing is potentially a very long horizon, and you can process amounts of data that exceed the ability of a human to process within a human lifetime. And there are nice examples of this, like like AlphaGo has many human lifetimes of experience. Some of these big language models that are being used in AI systems, at one point I sort of calculated it out, and they have the equivalent of like thousands of years of continuous speech, right? They are not constrained in terms of computation, in the sense that you can, wire up more and more processors and sort of dedicate more processors to your problem as you need them. And they're not constrained in communication in the same way, in that you can just like copy a state from one machine to another directly. You can make a tally of all of the data that's been seen and sort of transfer those data. You can imagine pooling data across many systems. Like here I think about like things like the Google Arm Lab, where they have many robot arms that are simultaneously manipulating objects. All of that data can be integrated onto a central server, right? It's kind of like if you could just work with your collaborators on a project and just like each one of you could read a paper, and then by the end of the day, you'd know the contents of all of those papers. That'd be great. So those, yeah.
Just to, so it's not that they don't face limitations, right? Obviously, they do face certain limitations. They're just crucially different limitations, and often fewer limitations than the one we face along all three of those dimensions.
Yeah. So I mean, the point here is that like your outlook and the computational problems that you face as a machine are potentially quite different from the computational problems you face as a human as a consequence of those constraints, right? And for that reason, we shouldn't, at least a priori, have a strong expectation that machine intelligence would look anything like human intelligence, right? That machines are going to be good at doing certain kinds of things, but they might be good at doing those things in ways that still seem very alien to us, because the kinds of solutions that are available to them are very different from the kinds of solutions that we have to use as human beings. And so like the AlphaGo example is a good one, right? Where, that system would play moves that to a human were very unintuitive, right? There didn't seem to be any underlying goal to them, right? And in fact, the reason why it played that move was just that, 25 moves into the future, it would be half a point ahead, right? And so,
I'm sorry to interrupt you. I just want to, in case, but both for myself and for the audience member that might not be super familiar with it. So part of the idea is that the way we decompose things into sub goals is dictated by the particular constraints we face. And so in looking at something like a Go move, we might be able to form an inference if it was a human player about what the sub goal is that they're pursuing. But if the machine is thinking about the total goal of just win the game and doesn't decompose it into some goals in the same way, each individual move wouldn't necessarily be intelligible.
Yeah, and one of the sort of counterintuitive things about this, right, is that some of the stuff that we consider fundamental to intelligence is a consequence of the way that human intelligence is constrained. Like if you look in the artificial intelligence literature, it's like, okay, the Newell and Simon sort of approach was like, we need to make machines that can figure out good sub goals, right? And then we'll, be able to get these sub goals. And well, you only need sub goals if you can't see all the way to the end of a problem, right? And so it's true that that's going to matter. It's, it's not like, every problem that our AI systems need to solve is necessarily going to be something that they can solve with the computational resources that they have. But there are going to be classes of problems that they can solve as a consequence of their greater computational resources that are just not going to require them to form subgoals in the way that a human being does, right? And so some of these things that are sort of seem like intrinsic aspects of intelligence are really kind of like consequences of the constraints that human minds operate under. And
the same would be true of the inductive biases and ability to learn from sparse data that you're focusing on with Bayesian. Yeah. So there's this kind of, the strongest version of this is, so we've been talking about priors and inductive bias and so on. So priors and inductive bias, what those things are about is basically setting us up with expectations about the world such that we're able to learn from small amounts of data, right? So now we can see one or two examples of a new concept, know what that concept is. It's great. Rapid learning, that's something that humans are really good at. It's still a challenge for machines. But there's a sense in which, machines should only try and emulate that human capacity to the extent that they're actually going to exist in those sorts of sparse data regimes, right? Humans intrinsically exist in those regimes because of the timescales that we operate on, whether those are, we need to learn a lot of stuff in our short lifetimes, or they're, we need to quickly figure out that thing over there is going to eat me, right? You don't get to do a lot of redos on that kind of learning in a way that a machine might, right? Yeah. And so as a consequence of needing to solve those certain kinds of problems, humans need to have strong inductive biases. We need to have good prior distributions and so on. If you're a machine and you live in a world where you're not under that same pressure, then your inductive biases matter less, right? And if you look at recent kind of trends in AI and machine learning, those trends have been towards, rather than engineering intelligent inductive biases into machines, it's more like you try and make the machines as flexible as possible, but also as quick, compute and drive
as quick to do computations as scalable as possible. And then you turn up the knob, which is the amount of data that you have, rather than doing, in many ways, it's sort of alternative challenge that we still are grappling with of figuring out how to instantiate the right inductive bias.
Yeah. Okay. I want to go back a little bit to this question of just sort of how that comparison is different than this prior comparison that we're doing between ourselves and animals. And you have this wonderful line in the paper where you say, rather than being animals that think, we are animals that think, and that's sort of the illuminating distinction there. I just have you elucidate what you mean by placing the emphasis on the different words there?
Yeah, so I mean, the idea there, right? So the sort of classical notion of animals that think puts the emphasis on, like reason, right? Thinking as the thing which is distinctive. And so now we live in a world where there are other things that, by some measures can reason, can engage in some kind of thought. And so if we are in this future where we have our super intelligent machines, the thing that's distinctive about human intelligence is that we are operating under these constraints, and those constraints are largely biological, right? In the sense of, they're just like a consequence of the fact that we are made of the same stuff as animals rather than made of the same stuff as machines. And so I like that conclusion. It sort of, I think, should be humbling in a certain kind of way, in the way that we approach things as humans. It also is, so some of the work that I'm doing at the moment is actually kind of going back and revisiting that, and also asking the question, well, how useful is this kind of framework for understanding what it is that makes us different from other animals as well, right? So you can think about this as, it's not just that humans operate under some constraints and machines operate under other constraints. It's also the case that other, intelligent species operate under their own constraints. And by making a better picture of what those constraints are like and what their consequences are, we could actually potentially understand not just differences between humans and machines, but also, more about the diversity of intelligences on Earth. And so, like there are meaningful ways in which humans differ from other animals too, in terms of those capacities for communication in particular, right? And those meaningful differences are things that might also help us to pick out some of the things that are unique about humans with respect to that sort of classical reference class.
So tell me if this is like an example. If we are sort of outsourcing more of our cognition, so humans have this quality of being neotenous, right? That we come out of the womb very, very dependent, and then we spend more time learning about things from our culture, because more of the information that's going to be relevant to our survival and fitness is sort of comes from the culture rather than being the kind of thing that we could represent innately. Is that the kind of picture that you have in mind?
Yeah. So it's that. So if you think about what communication does, communication is potentially a mechanism for overcoming the first two constraints that I talked about, right? So the first two constraints were limited time and limited computation, right? So limited time fundamentally means limited data. Limited computation is sort of, a limit to what we're able to, the resources that we have as individuals. Okay, so how do you solve that problem? Well, if you're a computer scientist, the way that you solve the problem of, not being able to finish the computation in the time that you have, not being able to process the amount of data you want to be able to process, not having enough computational resources, is you get another computer and another one and another one, and you hook them up and you build like a parallel network, a distributed, and you start using distributed computation, right? And you can think about the human case actually as doing something similar, right? It's just that we do that with much lower bandwidth, right? We do it with our communicative bandwidth. But things like, if you want to overcome the limits of the amount of data that you can get as a single human being, you can do that by writing things down, right? And creating sort of mechanisms of cultural transmission of information so that knowledge can be accumulated over successive generations, right? So that human Go player is not just relying on the experience that they have in their lifetime, they're relying on the distilled experience of past human masters who've written that information in a book that they can then read, and then sort of like, and pedagogical practices that are designed to get that information into their head as efficiently as possible. If you're thinking about limited computation, right? The way that we solve hard computational problems as humans is by doing things like forming companies or research groups or whatever it is, right? Like we put our heads together and that gives us more computational resources for tackling what otherwise would be something that might be an insurmountable problem for an individual. And so those, I think you could make an argument that those modalities of distributed computation are things that are an important characteristic of what it is to be human and how it is that humans overcome some of these problems in ways that maybe discriminate us from other kinds of animal species.
Mm. One more that comes to mind, and maybe this actually gets folded into the 3 limitations that you mentioned in the paper, but it does seem that another thing that we can do that animals can't is have these sort of represents things that are kind of causally distal to us. So like, we have limitations on time and communication. We also have limitations on like what we can be causally efficacious toward in our behavior, right? We're only sort of bumping up against our local environment.
Yeah.
We want to be able to represent things that are remote in time and space that aren't bumping into us, nor can we bump into them. Does that get folded into the first 3, or is that kind of its own limitation that might inform why we say have like, we can semantically represent things that are, you know, on the other side of the world?
Yeah, I think that's a good kind of, not one that's on my list, but it's sort of it's a consequence of being physically embodied, right? And I hadn't thought about that as shaping our computational problems, but it clearly does, right? And in particular, it seems like a relevant way in which it shapes them is exactly what you're saying, that like there's sort of only a point in being able to think about far off objects if
you can't bump into them.
Yeah, well, that's right. If you're connected to other people, right?
Oh, interesting. Okay.
Yeah, like you know, like part of the reason why we might care about climate change is because of the consequence it has for future humans, right?
So when you say connected to other people, you mean like normatively connected? What do you mean there?
No, I mean connected, like in the sense of like, you know, we're building our cultural, we're thinking at a cultural scale rather than at a individual scale.
I see. Okay.
Yeah.
Interesting. Okay, so do you have we're about to hit an hour. Do you have like say to 10 more minutes or
I'm good.
Okay, cool. I just want to make sure to sort of take some of the stuff we've been talking about, understanding human intelligence and the difference between human intelligence and machine intelligence, and apply that to some of these questions that people are thinking about with respect to AI alignment and how we can align our interests with machines, both the kind of near-term questions about ethics and bias and recommendation algorithms and the systems we're dealing with today, but also longer-term questions about super intelligent AI. And I guess this is to circle back to the thing I was sort of alluding to before about whether if these constraints that sort of drive how we solve computational problems are sort of constitutive for what we do as humans, how we think as humans, not just the not just the means, but also the ends. Is sort of AI, I guess, what's the not too vague way of posing the question? If AI systems don't share any of those limitations, what does it mean to align them with our ends if sort of the world that they inhabit and the goals that they're pursuing will be by definition different because the limitations that they face are different? Does that kind of make sense?
Yeah. Okay, so so a good example of this, I think, is like we talked about this explore exploit trade-off. We sort of alluded to this. It's like if you have
I don't know that we did, but it's in algorithm to live by. And so,
Well, no, I alluded to it where I said like you have to, within that lifespan, learn the things you're going to learn, but also do the things that you got to do, right? So the explore exploit trade-off is basically, you know, if you're going to live 80 years, you're going to spend, you know, some of that time acquiring skills and then some of the time using those skills, right? So I think, you know, like in a caricature, you might imagine, you know, childhood is your explore period where you're just exploring the world and sort of learning how the world works. And then the knowledge that you acquire there is what you're going to then use in your adulthood to then be able to survive and gather food and, you know, do all the things you need to do as an adult, right? So you sort of make this transition from exploring to exploiting. Okay. So the point at which you make that transition from explore to exploit depends on the horizon that you're operating over, right? So if you have an 80-year lifespan, right, maybe you transition at 20 from exploring to exploiting or whatever it is, right? And it sort of depends how much there is to learn in the world that you're in and so on, but you would expect that to scale, where like if you have a shorter lifespan, like if you're only going to live 25 years, it doesn't make sense to spend 20 years like, you know, learning stuff that you will then use for 5 years, right? Unless there's a very extreme sort of competitive situation involved in those last 5 years, right? And so the sort of the horizon that you're optimizing over is going to determine where you make that transition. Now, if you're a super intelligent machine, which is going to live, I don't know, it's not clear what the horizon is you're operating under.
Or like time isn't the same kind of
Yeah,
way if it's running
yeah.
fast.
You don't have a time scale that's imposed in the same way. That's right. So then, it's very natural to think that your point at which you make that transition would be very different, right? And the kinds of algorithms that you want to think about for learning about the world are going to be different, perhaps. One context in which I think you can see that is I kind of think about like corporations as our proxy for super intelligent machines, right? So like, a corporation is an entity that transcends individual humans, can have goals that go beyond those of those individual humans, and can execute at a scale that's beyond what humans can execute at, and arguably operates at a different time scale, right? Like if you're a cultural organization or a company, you can be planning on a different time scale than an individual human life. Right?
And that's fair to think about as being sort of analogous to the human scale versus like the neuron scale or something like that too.
Yeah,
right?
yeah, that's right. Yeah, so I think those kinds of timescale things are just one place where you might sort of naturally expect some misalignment. It's not a kind of misalignment that I think immediately you can identify scary negative consequences of. But I think it's at least an illustration of how being different kinds of entities can make you approach the world in different ways.
But mightn't it be the case that if there's sort of no, does that mean that alignment is a sort of a matter of making the limitations faced by machines more similar to the be faced?
No, I wouldn't say that.
Okay.
So this is an interesting question.
Okay, so I'm getting at whether if you want to think about terminal goals,
yep,
is it also the case that the terminal goals are sort of necessarily defined by these limitations, and therefore that you have to, if you want to align terminal goals, you have to align limitations?
So I think the answer, not thinking about it carefully, but I think the answer is no, and I think you have to have aligned limitations. But I think this is a really good question, which is, if you have a sort of heterogeneous community with respect to limitations, but you agree on terminal goals, whether that's sufficient.
Well, I mean, yeah. Humans sort of have means and ends preference, right? So, like, yeah. I mean,
so I can give you some examples.
There are a lot of versions of the alignment problem that sort of are recast in this limitations light, but I think it's super interesting. But like things like, you tell the car that you want to get there as fast as possible, and then you end up with vomit all over this is the Stuart Russell favorite example, right? You vomit all over the walls, But there's a means and ends thing. And if an alignment is sort of about both, how much does that converge on analogous limitations on time, compute, and communication, say?
Yeah, I mean, so I think you can definitely come up with examples which are positive examples where this is not an issue, right? So, like I was talking with, so I should say Brian Christian and I, Brian's my co-author on Algorithms to Live By. We've been working on an audio series with Audible that's about distributed computation.
Awesome.
So
we actually interviewed him as well about his alignment problem book too. So.
Okay, yeah. So as part of that, we were talking to people who run CERN, the sort of giant European physics lab, and the director of the experiments there was saying that one of the problems that he sort of anticipates is that you get to a point where you start running experiments that are going to sort of take longer than a human lifespan, right? And so how do you motivate the graduate student? You're like, oh, let's start this project. It'll be done in 100 years. We won't get results until then, right?
I mean, that's like, sort of directly analogous to what you were talking about with climate change too, right? It's like,
yeah, that's right. So how do you motivate a scientist to like commit to a project where they're not going to find out the answer to the question they're working on because they're going to die, right? Like, they're sort of guaranteed to die before that information comes out. but that's a problem where, again, like if you have machines that are not subject to the same constraints, everyone can agree, oh, we'd like to answer the scientific problem, but the machine is potentially more, not subject to the same kind of constraints of mechanisms of motivation for answering that problem. And so you end up with a class of science problems, which are kind of like, okay, those are the ones that we're going to get the robots to work on because the humans are not able to do those.
Yeah, but I wonder if that's also a matter of kind of aligning it with higher order goals that we do in fact have, even if we can't always make them motivationally salient.
Yeah. No, that's right. That's what I was saying. That's a positive case, right? Because everyone can agree that's the outcome that we want. It's just that we wouldn't motivationally be able to achieve it as individual humans. Yeah. Right. And so like most of the cases that I think about are really much more about how do we help humans fulfill their goals using computation than about, like, it's hard for me to think of a case where there's a clear divergence as a consequence of this. But like, so a lot of the work that we've been doing in the lab lately is saying, okay, if some of the weird things that people do are a consequence of not having enough computational resources, how do we solve that problem? Well, we can't put a chip in people's head. We're not going to do that. We're not that kind of lab. Yeah. But what we can do is we can put more computation into the environment that people are in, right? And so the way that we can do that is by sort of like pre-computing parts of the problem that people are solving in a way that then we can present people with the information in a way that makes it easier for them to make a choice. So we have a couple of versions of this. We call them like optimal gamification, which is kind of like using some pre-computation to structure rewards for solving a problem, or another one, which is optimal nudging, which is using pre-computation to structure the costs of gathering information. So you're sort of making it easier for people to gather the information that they need in order to make an effective decision. And so those are cases where we can kind of use the AI to help a human ultimately make a decision by just offloading some of the computation that the human would have to do otherwise.
Which we're already doing that kind of with all of culture and with, the reason why we'd use Arabic numerals rather than Roman numerals is because like there are all sorts of ways in which we're trying to do that. We're like sort of simple.
Yeah, that's right. That's right. And it's you could think about it from that perspective as like generic mechanisms of cultural evolution are trying to exactly like create representations and other sorts of objects that make it easier for us to despite the constraints that we operate under, be able to solve as wide a range of problems as we can. But maybe we can actually sort of dedicate some compute to that process, right? And do it on a much smaller timescale where it's not, okay, what are the best numerals to use, figured out over hundreds of years.
It's like accelerated cultural evolution within the machine to deliver us the kind of efficient representation.
Yeah, but and it's on the time scale of like you start interacting with the system, and then the system kind of learns something about you, and now is able to present information to you in a way which makes you more efficient, right? And so it's exactly encapsulating something like that process of cultural evolution. So, I guess if you have a negative view of this, the concerns you can have there are things about taking away aspects of human agency, right? And if there is misalignment where you're sort of wrong about what the human objective functions are, right? You have to make some inferences about what it is that humans want. So I can imagine lots of ways in which that can go wrong, but I sort of stay more oriented towards those sort of benevolent interactions rather than worrying about the all of the terrible things.
Nightmare scenarios, right? Yeah. Okay. Just one before I get off this topic, just one more sort of relevant thing that seems to come up from this idea about understanding human intelligence through human limitations and the way we differ from AI systems. Like this, correct me if I'm wrong, but this sort of goes all the way down to the level of just like the kind of ontology of the world, if not the way the world is, but certainly the way we like parse the world into objects. Is that fair? Like, certainly if you look at like what a neural network sees, it doesn't look like a world full of discrete objects. And in some sense, we register the world as in terms of objects to make the problem more tractable for us. And it's sort of, it's part of our sort of inductive biases, right?
Yeah, so certainly, right? I mean, you could argue that the fact that the neural network doesn't see things that way might be a consequence of us not giving the neural network the right kind of tasks, right? So,
Right. Okay.
what neural networks learn is fundamentally a function of what we ask them to do. And so, if we just ask them, tell me if this is a dog or not, it doesn't need to have formed
Right.
object representations in order
But
to
it's
do that.
analogous to the sub goal thing too, right? Like
Yeah,
almost it's like parsing the world
yeah.
into objects is like parsing it into sub goals.
That's right.
Yeah, yeah.
That's right. So there's this kind of like classical computer vision approach, right? Which is like, okay, so the first thing we're going to do is we're going to segment. And once you got the segments, then you can do this, then you can do this, and you can do this, and you can do this, right? And so one of the changes that's happened in machine learning is this move to what are called end-to-end systems, right? So an end-to-end system, instead of the human engineer sort of making a sequence of decisions about what features to represent and what pre-processing to do and how to transform this image and then feeding it into the machine learning system in an end-to-end system just gets the image at the start and produces the answer at the end. And then the sort of counter engineering inductive biases result of this is that, if you get enough data, the machine learning system can come up with better features than the features that the human engineers have identified, right? And end up doing a better job of solving the problem than the system which sort of is working off the representations that the humans are feeding it through their sort of careful thought about how to represent these problems. And so, yeah, I mean, I think there's a sort of pessimistic conclusion there, which is, we as humans have certain kinds of inductive biases. We have this way that we see the world, and we're kind of wrong about that being the way that you need to see the world in order to solve, some of the problems you want to be able to solve.
Right.
I think there's another way of looking at which is what I was saying, which is like, it might be that you need to see the world in that way to solve a broader class of problems, the ones that are actually the kinds that humans need to solve, like picking things up and figuring out how to interact with things and how to build things out of other things, and like there's a whole set of things that humans do with objects that means that knowing what an object is relevant. But I think consistent with the point you're making, yes, this is kind of like it's a mismatch between the human computational problems and the machine computational problems in a way that has direct implications for what the solutions to those problems look like.
And implications for sort of explainability too, because it wouldn't explainability then come at the cost of sort of honoring the richness of the world by not parsing it into these kind of chunks that make it explicable.
Yeah, and that one of the things that people who work on interpretability do is try and put some of that back into these models.
but I guess part of what I'm asking is, like, does that necessarily come at the cost of effectiveness?
I see.
Because it comes at the cost of what you were just saying, of the machine, in virtue of not being limited by computational resources, can sort of deal with a more complex world,
right,
and pick out features that we couldn't hope to pick out.
Yeah. If
we then try to make it explicable, is that coming at the cost of dealing with that complexity?
Yeah. So I don't know. I mean, I think you can. I think you can try and have the best of both worlds. And I think like the human case is probably actually something like this, right? Where there's a way that we experience the world and there's what's actually going on. And they're probably somewhat related, but not identical. And so you can imagine something like that for our machine learning systems too, where there's a way that they're solving the problem, and then there's the sort of explanatory layer, which is operating over the top of it. And you're not constraining in that explanatory layer what the underlying thing is doing. Maybe you're providing some information that feeds back into it, but you're allowing it a little bit of flex away from the sort of interpretable, explicable thing that you're doing.
I'm surprised this didn't occur to me before, but I'm now realizing this is sort of exactly analogous to the human case, as like somebody like Lucy Suchman would describe it, which is that like when we then say, when we explain what we're doing, it's so that we can be accountable, not actually explaining the concrete things that we're doing.
That's right. It's like you have the interpreter.
Okay, I have one more question. You've been super generous with your time. I really appreciate it. Just about what if you don't have the time, I'll let you go. It is in fact one question.
No, it's good.
Okay.
Yep. And I was going to say on that interpretability front, we have a paper where we did something like this for psychology. So basically what we did was we were trying to make sense of this data set that's called the moral machine data set, which has like,
I just spoke with those people too,
okay, great.
Yad and
yeah. So they have this massive data set. It has like tens of millions of people's judgments for trolley car problems, right? And so what we wanted to do is to figure out, okay, can we predict what choices people are going to make for a trolley car problem, and also can we understand what's informing those choices? And so what we did was we built a neural network model, trained the neural network model on the moral machine data set. We got some predictions out of that. And then we also built a kind of like theoretically informed psychological model, one that said, okay, you assign some utility to each kind of human life, right? And then also had some extra principles in it, like people don't like to swerve, right? So you have an extra cost for if you get to, if this sort of accident could happen,
like an omission commission bias.
Yeah, that's right. And we also had something for like legal versus illegal crossing, right? So these are sort of already documented effects. And we put all of these into our psychological model, and the best psychological model we could build still wasn't doing as well as the neural network model. And so now the question is, okay, how do we make our psychological model better? A standard psychology way of doing that is you look at the residuals, right? So you say, okay, we'll look at our psychology model and we'll see what it's, what are the biggest deviations from the theoretical model that we have. But when we look at those, it's really hard to figure out what's going on. And it seems like, in fact, when you have like 10 million human judgments on, trolley car problems, the biggest residuals are just cases that are weird and just like something weird happens, right? And so, so looking at the residuals wasn't helping us. And so then we had this other idea, which is, what matters is not, so a residual measures where you're the most wrong. And what matters is not where are we wrong the most, it's where did we go wrong that we could have avoided going wrong, right? So we call this approach scientific regret minimization, right? So we want to minimize the regret that we have about making an error. And a guide to where we could have done better is exactly the predictions that come out of that neural network model. Because the neural network says, okay, this is a case which you could have predicted, right? Because my neural network predicts it, but you didn't predict it. And so those are the cases that you should focus on to make your theory better. And so you can kind of use the neural network, instead of counterintuitively, you throw the data away, you take the neural network predictions, and then we compare the residuals between our theoretical model and the neural network predictions. And that neural network is essentially sort of smoothing out the data and taking out the noise. So we can prove mathematically, we show in this paper, that it's called scientific regret minimization. We show in this paper that that this is actually gives you more accurate residuals for your model. To there's a point where having this sort of black box model allows you to get a better estimate of what's wrong with your theory. And we use that to then figure out, okay, here's all of these really subtle features that people are paying attention to that we would never have discovered had we not done this. Like it matters whether okay, like you get these high order interactions, like crossing legally or illegally doesn't matter if you're a kid, but it does matter if that kid is with one adult.
Very
right?
interesting. Okay.
Yeah, and like sort of like these very fine sort of nuanced things that make a lot of sense.
You're almost like recovering like situatedness, right? Like, and like the kinds of ecological judgments that you might make if you were really in a very particular circumstance. You're almost like
that's right. Yeah, and they're in the data, but it took the neural network to sort of find them, and then it took this process of critiquing our interpretable theory to then be able to pull them out of the neural network and say, oh, here's a thing. And then we ran a bunch of experiments that replicated these phenomena. So I think that's a model for like A, kind of having this dual uninterpretable and interpretable system side by side, right? And B, kind of like being able to, again, like use the machine intelligence to augment the human intelligence, because we still had to figure out, okay, well, what do these meaningful errors correspond to in our model? But it gave us the information that we needed in order to more efficiently form a theory. So like that paper, we end up with like 70 of these factors. It's equivalent of like doing 70 psychology studies, right? So we're able to pull out using this one kind of model.
Yeah, so it wasn't kind of interpretable what it was doing a priori, but it pointed you in a direction that made you able to then.
Yeah, that's right. And I think there's lots of potential to do that in lots of other areas of science too.
Very cool. Okay, this last question I wanted to ask is sort of more particular interest to the psychologists who will be in the audience and the other social scientists who will be in the audience. But you've sort of famously made this call for we talked about the cognitive revolution. Part of the reason I had you give that sort of part of history is because you made this call for a second cognitive revolution. And I'll have you sort of introduce what that general idea is, but the particular sense in which I'm interested in it is relevant to these nearer term alignment questions, because part of what goes wrong with, say, something like a recommendation algorithm is that it is sort of pattern matching you to the behavior of other users and your prior behavior, and therefore creating a sort of more and more constrained vision of what kind of thing you could be. Whereas if you were to inject a sense of what the intermediate cognition is that's giving rise to that behavior, you might actually be able to build richer recommendation algorithms that don't have this sort of constraining effect on human behavior and radicalizing effect on people and things like that. So yeah, just have you introduce that idea of what you mean by a second cognitive revolution, and then we'll talk about the alignment implications.
Okay, so I mean, at a high level, the argument that I was making in this paper is basically that we as scientists are underutilizing the potential of technologies. That I think the observation that led me to this was actually, this was like when my first daughter was born. My wife Tanya Lombroso, who you've also interviewed, and I
in that case it was Juliana. But yes, we have.
We had an app we were using to keep track of our kids. Like, you could log like sleep and eating events and all of these things. And because we were handing the baby back and forth, this was like super useful. You could basically have this record and you could figure out how long ago various things had happened. And so when the baby, which is not a very interpretable system, was crying, you could be like, okay, this list of things. Oh, okay, it's this one, right? And figure out like what was most likely to be the fault that had generated that error message. And so, but I realized like the people who created this app just had more data on like infant behavior than the entire history of developmental psychology. And I was like, oh. and when you start thinking like that, you start to recognize, in fact, that's replicated like all over the place. That there's far more data about human behavior in industry than the entire history of psychology, and we don't have access to that data in many cases, and we're not necessarily thinking about using those data as much as I think we should. And so
nor are they. They're making use of it, but they're making use of it with these behaviorist models too.
Yeah,
right? Yeah,
that's right. And then so that's the second part, is then the need for, again, another cognitive revolution, is that the way in which those data are typically used in industry is, as you were saying, sort of in this behaviorist way of like, I'm gonna map stimulus to response, right? Of like,
and with the shaping goal,
what's the probability that someone's going to click on an ad? And the model that you use for that is not a cognitive model, right? It's not about internal states. It's not about cognitive processes. And so I think there's a potential that goes in both directions, in terms of there's a lot that we as cognitive scientists can learn from these massive behavioral data sets, and there's potentially a lot that cognitive scientists have to bring in terms of putting the cognition back into the way that we approach building these kinds of models. And then there was another part of that argument, which is also just about things like crowdsourcing services. So where like people were just starting to use Mechanical Turk and other kinds of systems for running experiments, but then the way that we've been doing it is we just run the same experiment we'd run in the lab, except we run it like 10 times faster, or maybe like twice as large or something like that. And again, that's underutilizing the technology, where really what we should be doing is saying, okay, now I can run this experiment that I would have run with 100 people. I can run an experiment with 10,000 people. Maybe if I can run an experiment with 10,000 people, I shouldn't run the same experiment that I would have run with 100 people, right? And so thinking about how does that change the approach that we take to doing science? And so just in the last year, it's funny, like I wrote that manifesto 5 years ago, and then in the last year, we've just been publishing some of the papers that have come out of thinking in this way. We had a paper in Science a few months ago where we looked at we looked at risky choice. So just like, how do people make decisions between different gambles? There'd been about 300 different scenarios that had been run in the history of previous experiments, and we ran 10,000 of them simultaneously. And then from that, get a much bigger data set that we can then, interrogate using some of these machine learning sorts of methods. We ran like some big Dunning-Kruger studies that allowed us to estimate exactly what the form of the function is that relates people's confidence to their performance in a way that allowed us to differentiate different kinds of cognitive models. We ran these insane experiments where we had people basically playing a game of telephone with a dot on an image to allow us to figure out the very sort of fine-grained specific details about how people represent images. And so these are all examples of like, what do we do when we have 10,000 participants? We change the way that we think about doing experiments. And so that was the second part of that.
And I guess you could say the scientific regret minimization paper is kind of in this vein too, right?
Yeah, that's right. It's about asking this question. So one of the things that comes out of this that's a subtle thing is more data means a different kind of theory, right? Mm-hmm. So we as psychologists are used to making relatively simple theories, which is the right thing to do when you've got limited amounts of data. But as you get much more data, you can find more systematic patterns in those data, right? And those are more likely to be actually true, right? Supported by the data that you have. And so you're justified in postulating sort of more complex theories in a way that ends up perhaps seeming a little unsatisfying for those of us who are used to being able to have like a sort of very simple, perhaps very elegant kind of explanation.
Yeah.
Now we have to deal with the complexity of the data that we're working with.
And am I right in noticing a strong analogy between the sense in which humans might want to have particularly strong inductive biases when they're dealing with sparser data? And I mean,
no, that's exactly right. It's the same thing. It's the
subject matter and the way of studying the subject matter. It seems. Yeah. Okay. I mean, the only other thing I wanted to just highlight there was that many of the issues that people have with the way companies are making use of these, say, recommendation algorithms, is that they have this constraining effect on people's behavior because they take this sort of behaviorist approach to thinking about human beings, and therefore, try to make your later behavior more like your earlier behavior, and they try to make your behavior more like the behavior of people that are similar to you, and end up, in a political sense, they might radicalize you, but they also just might make you just a more and more narrow and boring person. Whereas the richer the kind of cognitive model you could put in between the stimulus and the behavior, the less a constraining effect that would have, right?
I think you could imagine that. I mean, the most
or the better the manipulation. I mean, it's sort of
I think it could go both ways. I mean, I think the most basic version of that would be like just a simple fact from psychology, right, is that we ourselves are bad at anticipating our future desires and mental states. And so modeling people as what a computer scientist would call a restless bandit rather than a simple multi-arm bandit. So that is that we have a change in our state over time that would encourage more exploration behavior anyway, right? So there are some things that you could imagine doing where just having a little bit of psychology injected into the system might make things work better. We're also doing experiments in the lab where we look at what you can do to reduce bias in transmission networks. So sort of both documenting that. So we have a variety of results that show basically as information gets passed from one person to another, the potential for biases to influence that system increases. And then we're in the same vein as the other things I was talking about before, where we're sort of putting computation into the system, looking at how can you put computation into systems that are sort of like social networks in ways that reduce bias in information transmission. But in order to do that, you need to model individuals, right? So in order to like effectively reduce bias, you need to figure out what biases are there. And so again, it requires a little bit of cognitive modeling.
Okay, Tom, thank you so much for your time. This has been super informative and interesting. And I really appreciate you bearing with me as I sort of try to find my way through these questions, but I really, really appreciate it. Thank you.
Great, it's been a lot of fun.
All right, take care.